This is a basic arrhythmia class. Don't expect coming out of this class to become monitor techs. Okay, this is just basic enough for the NCLEX. All right. So I've never seen someone come back and say, "Oh, there was a question on the NCLEX where we never discussed in class." I never had that. So therefore, everything we teach must have been enough for the NCLEX. Yeah. Okay. So just basic. Okay. There are different variations of a rhythm. So when you look at it on one patient's monitor and look at another patient's monitor, they may not look the same, but it's the same rhythm. All right. So for fairness, I will only use strips that are on your textbook. So whatever strips are available on your textbook, that's what I'll use for your exam questions. If there are no strips for a rhythm, but it's on the textbook, I will only describe the rhythm as stated by the textbook. Are we clear? Any question? Okay, so only basic rhythms, the most commonly occurring dysrhythmias, and strips only available in your textbook. Are we clear? Yep. All right. Because a true arrhythmia class, if you want to be a monitor tech, is 3 weeks long. For the RNs, it's about 8 weeks. Okay, so long classes plus you have homework to do also before you get to the class. We only have 3 hours. All right. Okay, so let's go with the very, very basic. Before we go to the abnormals, let's look at normal conduction first. So what are dysrhythmias? Of course, we have to look at the normal rhythm first. So each wave and complex here is an electrical representation of what's going on inside your heart. So we'll look at what a cardiac cycle electrical conduction looks like, and then we'll look at abnormalities or deviations from the norm. We have 3 pacemakers in our body. What is a pacemaker? Pacemaker is a cell that generates an electrical impulse. Now, unlike the rest of the body, wherein all muscles depend on electrical nerve stimulation from the brain in order to function. For instance, that's why if a patient has spinal cord injury, what happens to the muscles below the level of spinal cord injury? It's now paralyzed, right? Was there anything wrong with the muscle? No. Nothing. The muscle was fine before the injury. But what transpired was there is a disruption of the electrical impulse. So no electrical impulse, muscles are useless. All right. The heart, however, doesn't work like that. The heart can independently generate its own impulse separate from the brain, meaning the heart really doesn't need the brain in order to function. It can generate its own impulse. We call that action potential. So these are only found in the heart. The heart is the only one that can generate its own electrical impulse. That's why if you have a brain dead person, the heart still continues to pump. Okay, we can keep them alive because they are 2 separate systems. Although the brain can influence heart activity, but it does not really control heart activity. Okay, it can influence it. You can raise, the brain can secrete hormones or enzymes that will raise and lower the heart rate, raise and lower the blood pressure in the process, but isn't really needed in order for the heart to function. So the 3 pacemakers are, the main one or the primary pacemaker is the SA node. This is located in the right atrium. 691. The primary pacemaker. So the SA node is located in the right atrium, right at the door. So it's capable of firing 60 to 100 impulses in a minute. This is represented by the P wave on the ECG strip. So we'll look at strips later, and we'll look at what the P wave looks like. The secondary pacemaker is the AV node. This is located at the junction between the atria and the ventricles, right at the door. Again, I'll show you a picture later. This is a secondary pacemaker, meaning If the SA node fires or fails to fire, or the AB node perceives that the SA node is not firing, the AB node can be a backup. It will fire its own impulses because it is a pacemaker. However, it can only fire 40 to 60 times a minute, less efficient compared to the SA node. The third, pardon?
On what side?
Say on what?
On what side is that?
Oh, the AV node is right in the middle where the septum is. I'll show you again a picture later. The third set of pacemakers are the left and right bundle of His all the way to the Purkinje fibers. Again, I'll show you a picture later. I will not bother talking about this function because they are pacemakers. However, they're only firing 20 to 40. So it's not worth talking about, meaning these set of pacemakers cannot sustain life. They're useless, okay, as a pacemaker. So we won't talk about it. It's not worth talking about. So a few terms here so you'll understand the next few pages. When we say depolarization, this means that as the cell becomes more and more positively charged, it will discharge all that energy. We call that a contraction or depolarization, meaning they will depolarize, making them switching them from very positive to now totally negative. We call that depolarization, meaning they will release all that pent-up energy. Repolarization is once a cell is now negatively charged, it will become positively charged again. Little by little, sodium and calcium channels will open, and then those electrolytes will go in, charging the cell in preparation for the next depolarization. Okay, so that's the cycle of every cell. So systole or depolarization or contraction, whether it's the atria or the ventricles, is called systole. Okay, so when they depolarize, and they repolarize during diastole. So if you think about it, the heart therefore contracting when it is receiving blood? No, because otherwise it cannot receive blood, right? If it's contracting, because yeah, the coronary arteries are meaning if you're contracting, the flow of blood really is going the opposite way. It's going away from the heart. So it has to wait during the diastole when the blood falls back from the aorta, entering the coronary arteries. Okay, so these are the hormones I talked about earlier. There can be influences by hormones on heart function coming from the adrenal glands, from the pituitary gland, meaning from the central nervous system. So what is an ECG? This is not, again, an ECG class. The ECG machine was invented by Dr. Einthoven, and he postulated and he proved it that when you put positive and negative electrodes to certain parts of the body, it will capture electrical activity, and this will be represented in a graphing paper. So he invented the machine as well as the graphing paper. We'll discuss more about the measurements on the graphing paper later. So this is your body, this is your heart. Since the electrical impulses travel from, this is the SA node, like I said earlier, located in the right atrium, right at the door. This is now the AV node, right at the junction between the atria and the ventricles, right here in the septum. And then these are the left and right bundle of His, and they end in the Purkinje fibers. So as you can see, because the heart is pointing to the left, meaning it's pointing toward your left foot, and these are the leads. Lead 1 is right on top. Lead 2 is on the right side of your heart. Lead 3 is on the left side. So that's why most of the, not all, but most of the leads you'll see on your textbook is taken from lead 2. Why? Because lead 2 is, if you look at it, the electrical impulse really travels from your right shoulder toward your left foot, correct? So since lead 2 is parallel to that, so it's the best representation of the electrical impulse. Because if you look at, there will be 12 leads in an ECG. That means the 12 leads are lead 1, 2, 3. That's the first three. Then we have the AVL, which is your left arm, AVR, right arm, and then AVF. AVF is the left foot. There is no lead on the right foot. The right foot is a ground lead, you know, because of electricity, you need a grounding lead, yeah. And then there are also so that lead 1, 2, 3, and then we've got the AVL, AVR, AVF. So that's 6, and then we have the lead 4, 5, and 6. Okay, I'll explain later when we get to the ECG placement. Yes. Okay, so if we have a 5-lead telemetry, Mr. Lewis is asking about a portable cardiac monitor. So that has 5 leads. Therefore, those 5 leads are not bipolar. So therefore, they will only give you 3 views. A 12 lead ECG has 10 electrodes, but they give you 12 views because 2 of them are bipolar leads, meaning those leads carry a positive and a negative. Again, I'm not here to explain all these concepts because it's not testable. You know, you need a separate ECG class to understand how an ECG works. Okay, so we're just here for this class to interpret the waves and complexes. Okay. So there are 2 meanings when we say lead. A lead can refer to an electrode, and a lead can also refer to a view. For instance, in a 12-lead ECG, right here, a 12-lead ECG has 10 electrodes. These are the placements. You have 6 leads in the chest, 1, 2, 3, 4, 5, 6, and then 1 lead in each extremity. 1 for the right arm, left leg, right leg. So that's 10 electrodes, yeah? But these 10 electrodes interact because, again, 2 of them have bipolar leads. So they will give you 2 views. So therefore, total, it will give you 12 views. What is the significance of the 12 views? Well, it gives you basically a 360 view of the electrical activity of the heart, meaning you can see it from different angles. Think of it as the human heart is a model, and you have 12 different photographers taking a picture from different angles. I don't have 12 lead reading here, but let's look up online. Okay, so this is an example of a 12-lead ECG. So you have here lead 1, 2, 3, and then you got AVR, AVL, AVF, B1, 2, 3, 4, 5, 6. You notice that this is the same patient, but there are 12 different leads or 12 different views. The same rhythm, however, they look different depending on which lead are you looking at. So this is what I mean by it's like 12 different photographers looking at it from a different angle. Look at AVL. AVL looks like this because really the line of sight, when you take an ECG class, the line of sight for the AVR, sorry. The AVR is actually taken from the left shoulder because it's a bipolar lead. So it's looking at it from here toward the right. That's why it looks like this. Whereas look at lead 2. Lead 2 is parallel to the electrical pathway. So it looks like this. This is the perfect lead to observe somebody's electrical conduction. Okay, so it looks slightly different here because again, this is from a different angle. And sometimes it's even inverted. Okay, so instead of looking like this, it will look upside down. For instance, in this lead. Okay, so look, if you observe the QRS complex is going this way, but in this view, it's going downward. Okay, because it's looking at it from a different angle. Are we clear? So we're not concerned about this because we are nurses. We do not do the diagnosing, but the doctor needs a 12-lead ECG to see where is the problem. Okay, where is the calcium or sodium channels or potassium channels not opening, meaning they can see where is the injury, okay, in the heart, where exactly. So if they see it at a certain lead, then that gives them an idea about which coronary artery is causing the problem. All right, and then it will help them plan which drug is best to treat it. Okay, again, this is not our concern. This is for the doctors. Our concern is the interpretation of the rhythm and then notifying the physician. So I'll stop up to there. Then let's go now to the interpretation. Before we do that, let's look at what does each wave and complex mean or represent. So the first wave is the P. This is the picture. So this is the P wave. First of all, let's explain the graphs. So the ECG paper has vertical and horizontal lines, yeah? And because of these lines, we have it formed small boxes and big boxes. So this is one small box right here. And this is one big box. Again, one small box and one big box. The horizontal axis measures time in seconds. I repeat, the horizontal axis represents time in seconds. The vertical axis represents voltage in millivolts. Vertical axis measures voltage in millivolts because this is electrical activity. So the P wave represents atrial contraction. Here, impulse is fired from the SA node, spreads through the atria because we have interatrial branches, meaning when the SA node fires an electrical impulse, it will go to the left atrium as well. You've seen lightning, yeah? Okay, we haven't really observed electricity, but we've seen lightning. How long did it take for that lightning to appear on the sky and then appear to hit something on the horizon? It was over before you knew it, right? Like diarrhea. When you have diarrhea, oh, it's already there. It's already in your pants. Ah, God. So it's that quick, okay? So same way, when the SA node fires, will it take a long time for that impulse to travel to the left side? No. No. So therefore, both atria will contract at the same time. No difference. They will contract instantaneously because that's how fast the electrical impulse started. So when we see a P wave, that's good, okay? Because what are the two meanings of a SA node? I mean a P wave. So when we see a P wave, that means where did the impulse come from? The SA node fired. And what did the impulse do? The atria contracted. Okay, so two meanings, right? So two meanings. We see a P wave, we're happy. Oh, P wave, great. Because we know the SA node fired. The impulse came from the SA node and the atria contracted. So therefore, if there are no true P waves or you don't see any P wave at all, is that good? No, because did the impulse come from the SA node? No. Did the atria contract? No. Okay, so do we want to see P waves? Yes, P waves are beautiful to see. Okay, So we measure each wave and complex by measuring them from when they, another concept we need to know is, this is a drawing. This is not a true tracing. Okay, so this is just drawn by an artist. Okay, we'll see actual strips on the next page, but there is a imaginary straight line from which every wave leaves and then returns. Okay, again, it's an imaginary straight line. Let me show you this one. Okay, so because the waves and complexes they never fall and return on a solid line. You notice this sample? See, this is what I mean by the waves and complexes never fall on a solid line. So you can just estimate a isoelectric line. We saw that, we call that isoelectric, meaning a flat, straight, flat line. So for this example, where can you put the isoelectric line? Somewhere here, right? So somewhere here is where each wave and complex leaves and returns. Okay. So let's go back here. Well, for all the waves, so you estimate which is a common point for them to leave and return, because you need that isoelectric line in order to measure the waves and complexes, right? So let's say this is it. So therefore the P wave starts here, ends here. So what is this again? The duration, right? Because this is time. Okay, so time in seconds. So for us to measure, we need to know how much does each box measure. Each small box right here, this small box, measures 0.04 seconds. Again, 0.04 seconds. So if you notice, a big box has how many small boxes in a line? 5. Okay, 1, 2, 3, 4, 5. So 0.04 times 5 equals 0.2 seconds. Okay, so therefore one big box is 0.2 seconds. Okay, so in 60 seconds, therefore, how many small boxes will there be? So 60 seconds divided by 0.04 equals, no, divided. 60 divided by 0.04. 1,500 small boxes. Very good. And since a big box is 0.2 seconds, so therefore, how many big boxes will be there in 1 minute? $60 divided by 0.2 equals 300. Okay, so hold this thought for now. Okay, so there are 1,500 small boxes in 1 minute, and there are 300 big boxes in 1 minute. We'll need this later when we count the heart rate. Okay, so keep those facts in your head first. Again, how many small boxes? 1,500 in 1 minute. And how many big boxes? 300 big boxes in 1 minute. Yes, Mr. McNair?
We need you to repeat that.
Oh, okay. Okay, so we know the P wave, and we know the P wave means what? Two things? The SA node fired and the atria contracted. Very good. Next measurement is, I won't go in order. I won't follow the textbook because I want to go in order. So P wave first. After the P wave is actually the PR interval. So let's go here. PR interval. What is the PR interval? We measure this from the P wave, meaning it includes the P wave, to the beginning of the QRS complex. Now, the QRS complex is here. So again, we measure each wave and complex from when they left the isoelectric line to when they return to the isoelectric line. Okay. Now, since the P wave started here, so we'll start counting here. Okay. And then since the QRS complex starts here, so this is the Q the beginning of the Q. So this is Q, R, S, and then this is the end of the S, because this is where it returned to the isoelectric line. Since the description is PR interval is measured from the P to the beginning of the QRS complex. So therefore, we measure the PR interval from the P. It includes here to right here. Okay, we can't include this one because this is now the Q. So we stop at the beginning of the Q. Okay, now that can be misleading, right? Because the R is way up here, but they call it the PR interval. Why? I have no idea. So to this day, I'm still wondering, why do you call it the PR interval? It does not include measuring the R wave. R wave is way up here. This is the the end of the PR interval. But I don't know what else to call it either. When you ask me, I ask them, why is it called PR interval? And they'll ask me also, well, what do you want to call it? I don't know. I can't say PQ either because it's not really including the Q either. So we have to call it something. So anyway, the PR interval. So that's where we measure it from here to here. So let's measure the PR interval. So since each small box is 0.04, measure this one. The PR interval is from here to here. So how many seconds is that? So I'll take a shortcut. I know this is 1, 2, 3 small boxes. Yeah, 3 small boxes times 3, 0.04 times 3, that's 0.12. But it's not 0.12 because I have here. So I have a half, right? So I have 0.02. So 0.02 plus 0.12 equals 0.14, correct? Okay. So this,
count the entire box.
well, this one's only half a box. Yeah, because this is time. Okay, we don't round. Okay. So the PR interval here is 0.1, because it's 0.04 times 3. I have 3. 1, 2, 3. Yeah. So that's 0.12 plus 0.02. So my PR interval is 0.14 seconds. All right, you follow so far? Okay, so let's look at what is the normal measurement and what does this represent? Since we measure it from the P wave to just before the ventricles contract, because the QR complex is ventricular contraction. So if you imagine the cardiac cycle, so this is the time it takes, therefore, for the atria to contract and before the ventricles contract. Yeah, because it's measured from the P wave to before the QRS complex. So therefore, it measures what time? Atrial contraction to before the ventricles contract. Now, what's the significance of this time? The normal measurement is it must measure 0.12 to 0.2 seconds. Okay, so what does this mean? What's happening, therefore, when the atria contract? What happens to the blood when the atria, they fill the ventricle? So can you say that this is ventricular filling period?
Yes.
Yes, because if you think about it, let's go back to our impulse on the previous page. I said, how long does it take for the lightning to appear and then hit something? Instantaneous. Okay. So if it was instantaneous for the SA node to fire and the electrical impulse reaching the left atrium, did it take any longer for it to reach the AV node? No, because if it instantaneously spread here, then what's the difference if it also instantaneously, it should instantaneously reach here, right? Okay, but if it did that, so let's say the electrical impulse went from the SA node to the left atrium, and they both contracted at the same time, why didn't the AV node transmit the same impulse? And if it did, then that would mean the ventricles will also contract right at the same time, correct? Because that's how fast it is. This is electricity, right? It would just get just like diarrhea, right there. So it wouldn't be a long time. So that would mean, will the atria and the ventricles contract at exactly the same time? Yes, that's what's gonna happen. However, since it did not, this is your evidence. Did the atria and the ventricles contract at the same time? It did not. So therefore, what did the AV node do? Very good. It delayed the impulse transmission. So that is the significance of the AV node. Why did the AV node delay it? Because if it didn't delay it, what would be the result?
The ventricles would be contracted.
The atria and the ventricles would contract at exactly the same time, which will be disastrous, right? Meaning, will there be any blood movement? No, because each one was contracting. So they will just bounce each other off, right? But that did not happen. So can you say that the AV node is like a gatekeeper? Yes. So besides it being a secondary pacemaker, it also has another very important job, which is a gatekeeper. It's going to delay. It received the impulse right away. But what did it do? It did not transmit. Okay, we received it. Okay, I got it. It waited first. For how long did it wait? 0.12 to 0.2 seconds. It waited. Okay, 0.12 to 0.2 seconds later, here you go. It transmitted the impulse from the SA node. You follow so far?
Yes.
Okay, so as long as the AV node is doing its job, this is what's gonna happen. Okay, so we'll have a P wave first, and then followed by the QRS complex. So this is now your QRS complex. Now, imagine the voltage. If the atria contracting only generates this much voltage, imagine the strength of the ventricles if they generate this much voltage, okay, when they contract. So this is atrial contraction right here. That's all it's generating. Look at the ventricles. How many times stronger is that? 1, 2, 3, 4, about up to 6 times stronger. Okay, so 6 times stronger electrical activity, electrical energy being generated. So what is the QRS complex? Represents ventricular depolarization. So the ventricles are contracting, right? And then the measurement is the width of the QRS complex is usually less than 0.12 or less than 3 small boxes. Okay, so that's why we do 3 small boxes and big boxes, so that we don't have to keep measuring, because we know, okay, I know a small box is 0.04 and I know a big box is 0.2 seconds. So if I just eyeball it, saves me time, yeah? So if I look at the strip, oh, I know this whole big box here is 0.2 seconds. So therefore, as long as my QRS complex is not more than 0.12 seconds, usually it's 2. So I know it's normal. Yeah, so just eyeball it because you have other S word to do. I don't want to have to spend hours looking at my patient's rhythm. Okay, so it helps you analyze your strip faster. And then next wave is the ST interval or ST segment. So what is ST segment? It is early ventricular repolarization, meaning the QRS hasn't really repolarized because the ventricular repolarization really happens in the T wave. Where is my T wave? Right here. So T wave is ventricular repolarization. So this is the T wave. Ventricles are actually repolarizing, meaning electrolytes are going in there, turning the cells, the ventricular cells, more positive, okay, getting ready for the next QRS complex. The ST is early. It should be isoelectric, meaning it should be flat. Okay, normally isoelectric, meaning this will make a difference now. So next semester, when we talk about heart attacks, so if somebody has a heart attack, that means did cells in the myocardium die? Yes, they died. So they will have ST elevation, meaning this QRS complex here, the ST segment, instead of flat like this, it will be elevated, meaning it will, yeah, it will repolarize right here. So that means, what does that tell you? Why did it repolarize too soon? Because some cells died. Okay, so the other cells cannot repolarize, so therefore you will see an early repolarizing wave. Okay, so the ST segment will be elevated like this. Okay, so that indicates an acute MI, acute heart attack. Okay. So what do we want to see on the ST segment? Should be isoelectric. Okay, what does this represent again? Early repolarization of the ventricles. The T wave right here is ventricular repolarization. So it's now the heart's not doing anything here, but it is repolarizing. So does the heart, when you answer the question, does the heart really rest? It does. Okay, so this is here. It's resting. Okay, for how long though?
0.12.
How long is this period?
This one.
So if one big box is 0.2 seconds, that's all it's resting. Okay, so it's about one big box and some change. Okay, that's all the rest your poor heart has. And it's been doing that for however old you are now. Yeah, if you want to give it rest, die. Okay, and then your heart will rest. All right. So those are the significant for our purpose. The other waves aren't really significant for our purpose. Like the QT. I won't test you on the QT, but let me just explain why the QT is significant. So when we say QT, that means it's from here to here, yeah? From the Q to T. If there is prolongation of the QT interval, because think about it, what's happening during the QT? So that means the ventricles contracted, yeah? And then they started to repolarize. So there's a time, yeah? So if we measure the time from here, Q to T, let's measure this one. So these are 1, 2, 3, 4, 5, 6, 7, 8, 8.5. 8.5 times 0.04. How much is that? 0.34. Okay, that's normal. Okay, so if it reaches plus there's a difference between male and female. So if it reaches, let's say, more than 0.35 seconds for female or more than 0.4 seconds for males, that indicates this patient may go into ventricular fibrillation. So is it, yeah, because is it good? No, that means this heart is injured, meaning the ventricles are very irritable. Okay, it suffered a serious injury, meaning have you heard of torsade de pointe? Okay, so that rhythm is prolonged QT. So when you see prolonged QT, they will go into a twisting. This is what torsade de pointe, it's not in your textbook, but this is what it looks like. It's a type of ventricular tachycardia. And when you see this, prepare for ventricular fibrillation. VFib will follow. So when we see that rhythm, we call the doctor or call rapid response because we know this patient has minutes before we go into VFib. This patient will code. Because VFib is basically cardiac arrest, yeah? Yeah, so this when you see this rhythm, so you see twisting, like a pretzel, twisted pretzel. So that's a sign that, oh, call rapid response, because we know what's the next thing is. It's going to be cardiac arrest already. It will be ventricular fibrillation.
Conscious?
Of course, no. I mean, there's no cardiac output. Now, the important thing here is because when it's torsa de pointe, we know it's going to be VFib, right? But the important thing is you catch it by measuring the QT interval. So you look at the QT. So when you see the QT being prolonged, no, 0 point, again, for female, more than 0.35, male, more than 0.4, then you call ahead. Hey, doctor, I have prolonged QT. Because this can be caused by medications, okay, so that you can check, okay, which medications are causing the prolonged QT, and then stop that, okay, and then observe the patient. That's about all we need. The U wave is not really there all the time. I mean, I personally have never seen a U wave. I've never seen it. Sometimes it's there, most of the time it's not.
Yeah, this is the wave found in
Hypokalemia, yeah, usually potassium imbalances.
also it's called secret.
Hyperkalemia, yeah, tall peak T waves. But this U wave, I've never seen it, honestly. I've never seen it. I see, you know, just a PQRST, but I don't see a U wave.
See, hypokalemia, like it's short T wave stuff.
No, what it's really just with the
Hyper.
hyperkalemia that we see a tall peak T wave. Okay, so let's start now with, so we know the basic, right? So let's review. What does the P wave mean?
That the signal expired.
Okay, so we know the atria contracted and that impulse was initiated by the, okay, as you know, so that means, is this heartbeat normal?
Yes.
Most likely. Okay, so when we see a QRS complex and its duration is less than 0.2, 0.112, is that normal?
Yeah.
Yes. Yes. And then we see an isoelectric ST segment. Yeah. And then we see a positive deflecting T wave. Okay, so we know the ventricles are repolarizing. Now, if the ventricles repolarize, that means the P wave must also repolarize, yeah? Okay, but it's probably hidden somewhere, because if this is the sequence, meaning after the ventricles depolarize or contract, then a millisecond later it will repolarize. That means, when will this atria also repolarize? Be somewhere here, yeah? Because it's so small, because look at the voltage if it's contracting. So how much more smaller will the repolarization be? It's probably somewhere here. Okay, we just don't see it. But of course, when we see another P wave, we know that it had repolarized. Yeah, we just don't see it because it's too small. Okay, let's go to our common dysrhythmias now. Yes.
So just the T wave, T wave, T wave one.
P wave, PR interval, and then the QRS complex, ST segment, and the T wave. That's it. Okay, we'll stop at counting the heart rate. We'll look at a few methods on how to count the heart rate, and then we'll look at dysrhythmias next week. Heart rate. So we will discover, or we will use 3 methods as written in your textbook. Since I don't know what methods you guys will use, so when I give you a strip, Stephanie may use, okay, she likes the big box method, she'll use the big box, or maybe Mr. Soler will use the small box, or Ms. Idini will just count the number of PQRSTs. Okay, I don't know which method, so I'll give you a range for the choices. Okay, for instance, if I give you this rhythm, this strip, I'll ask you, okay, give me the estimated heart rate. I say estimated because we only use 6-second strips. So all the strips you'll see in the textbook are 6 seconds. Why 6? It's impractical to print out a 60-second strip. So waste of resources. Plus, from minute to minute, will your heart rate really be the same? It'll vary, okay? So therefore, we'll just use an estimated heart rate using a 6-second strip. Now, how do we know a strip is 6 seconds? There are 6-second markers. 3-second markers on a strip. Show you an example. There are no good examples here. Okay, so I'll show you on the internet. Okay. So a strip will have markers on top like this. See these markers? These are okay, see this?
Yeah.
These lines on top? Those are 3-second markers. Are we really sure this is 3 seconds?
Yes.
Oh, no, that's not a 3-second marker. That's too it's a bad example. Yeah, but that's okay. This is a good example. Okay, this is a 3-second marker. Okay, that is a 3-second marker. That is a 3-second marker. That is a 3-second marker. Okay, so let's see. Is that really 3 seconds? So how many seconds is one big box again? 0.2. So therefore, how many big boxes in 1 second? 5. So let's count. So how many big boxes are there between this marker and this marker? It's 3 seconds. That means we expect how many? 15. Okay, so let's count. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Son of a bitch. It is 3 seconds, yeah? You agree?
Right on.
Yeah. Okay, so that's a 3-second marker. So if there's no marker, can you make your own? Yes, you just count 15 big boxes. That's 3 seconds. Okay. All right. So there are many methods again. So let's start with one. Because what is one cardiac cycle? What should we see in one heartbeat? We should see one set of PQRST, yeah? So we see one PQRST, that's one heartbeat, okay? So since this is time, so let's see, let's create our 3-second markers because we can only do, the good thing about 6 seconds is whatever number you get, you multiply that by 10, that's 60 seconds, yeah? So that's your estimated heart rate. So let's see. Let's put our marker somewhere. So 1, 2, 3, 4, 5. 1 second. 1, 2, 3, 4, 5. 2 seconds. 1, 2, 3, 4, 5. 3 seconds. So this is a 3-second marker right here. And then we'll put another marker here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, another marker here. So one marker here, one marker here. Yeah. So this is a 3-second marker, 3-second marker. So our 1 minute would be from here to here, yeah? I mean, no, not 1 minute, 6 seconds. So 6 seconds will be from here to here. You agree?
Yes.
Okay, so we'll measure from here to here. Okay, so we'll disregard the rest of it. So, can I count this heartbeat right here?
Yes.
No.
Is this a complete heartbeat?
No.
No, this is partial because it's missing. The P is not within this, so I can't count this. Can I count this one?
Yeah.
Okay, let's count this one. 1, 2, 3, 4, 5, 6, Can I count this? This is my 3-second marker. Can I count this?
Yes.
It's connected to the.
No, because the T is incomplete. Okay, so how many did I count? 1, 2, 3, 4, 5, 6. Yeah. Okay. However, since this is an incomplete heartbeat, but I'm also missing a P here. If I move it, because I don't really have to count here, right? So if I put this P here, can this now be in my 6 seconds? Yes. So do I have 6 or 7? 7. So what is my estimated heart rate? 70. Is it really 70 or is it 70 something? It's 70 something. Yeah. We don't know exactly. Remember, this method is only an estimate. What is my true exact heartbeat? If I have to print an entire 60-second strip, but I only have 6 seconds. So therefore, is it acceptable? Yes, estimate. Remember, these are estimates. The only true accurate count is a 1-minute strip. Okay, so that's one easy method. Let's go try another method. So we said there are how many small boxes in 1 minute? 1,500. Okay. In order to use this method, if we're going to count small boxes between an R and R interval, that means which one is the R wave here? These pointy things, yeah? These are R waves. Okay. So you're going to count the number of small boxes between 2 R waves and divide that into 1,500. Why did we get 1,500?
Because the small.
Okay, that's how many small boxes are in 1 minute. Okay, so let's try. Which 2 R waves do you want to count? Me ask Carolina. Give me 2 R waves that you want to count. This and this, or this and this, doesn't matter. Which one? Most people want to choose an R wave that's smack in the middle of a straight line, because that way, you know, it's easy to count. But doesn't really matter. It's up to you. Which one? You want the first count? Which R waves do you want to count? 1 and 2, 2 to 3. Number 6. So 1, 2, 3. Oh, you want to choose this one. Okay, so this one, 6 and 7, therefore, yeah? Okay. So between R wave number 6 and R wave number 7, how many small boxes are there?
Small boxes, no. 3.5? No. It's
Small boxes, small boxes.
in the whole box, right?
Yeah,
So
this is a this is a big box.
So all of.
There are 5 small boxes there.
So 20. So it's in a straight line, right? So 5. From which one to which one again?
This one,
5.
yeah, 6 to 7. Okay, so fastest way would be 5, 10, 15, 17 and a half. Yeah, it's not really 17 because it's in the middle between 17 and 18. Yeah. Okay, so it's again 5, 10, 15. And use your textbook. If it's hard to see here, use your textbook. I'm on page 695. So I counted how many? 5, 10, 15, 17 and a half. So 17 and a half, divide that into how many small boxes in 1 minute? 1,500 divided by 17 and a half. What did I get? 85, which is about 86. Yeah. Okay. Now let's look at big boxes. Which big boxes do you want to count? Let's see if there's a difference. Rebecca, which 2 big boxes? Which 2 R waves do you want to count? Don't use 6 and 7. Use another one. 8 and 9. So 6, 7, 8, 9. Okay. She wants to count this one and this one. Okay. These 2 R waves. Big boxes this time. So 1, 2, 3 and a half. So 3 and a half big boxes. How many big boxes in 1 minute? 300 divided by 3.5. What did I get? So is it the same? About the same, yeah? So you can use this method, any of the 3 methods we used. we may have counted the marker earlier wrong because our QRS, yeah, it was different, right? We did 70, so we must have counted it wrong.
The number.
It'll be the same,
So
yeah.
we made a mistake.
Must, we'll repeat again. What did I say? Okay, so you can only use this method if the rhythm is regular. Now, when I say regular rhythm, I don't mean sinus rhythm, because a normal rhythm is called normal sinus rhythm. By rhythm, I mean, you know, a music, right? Like, have you heard your favorite song? Let's say it's either the drum or the guitar has a rhythm, yeah? Every few seconds, they they pluck a certain string, yeah? There's a rhythm, yeah? So when I say that, I mean, if you use a caliper, but we don't have a caliper, but we have a poor man's caliper. Who has a pen or a marker? So when I say no, regular rhythm is, look at this R wave here and this R wave. So no matter where I put that, about the same. Yeah. So therefore, what can you say about this patient's heartbeat? Is it regular or irregular?
Yes.
It's regular. It's regular. So if the rhythm is regular, that means you can use any of those three methods. Now, if it's irregular, you're gonna have to use either the small box methods or the big box method. You cannot use the PQRS because from minute to minute, is it gonna be the same? No, your estimate will always be different from one strip to the next. But it's okay because again, if it's an irregular rhythm, is the heartbeat bound to be the same minute to minute? It's not going to be the same anyway. All right, so for the exam, what do I put on the choices again? If it's a heart rate question, I'll give you a range. Okay, I'll give you what is the heart rate here, estimated heart rate. Is it 80 to 90, 90 to 100, 100 to 110, or 60 to 70? What will you choose? 80 to 90. All right. Okay, let's go back because it's eating me up now. How did we get 70 something on the first one?
We counted, 'cause we added 7.
It
Maybe we should
moved.
do 6.
No, I think we counted the wrong marker. Somebody has a marker? Okay, let's do it by hand. So let's establish our 6-second strip. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. Okay, 15 will be right here. Can somebody mark this? You have a booger or something? Maybe a booger?
So tip of the mouse there.
Oh. Take it.
Bring the chair.
Where did we say it was?
It was 3 boxes before.
4, 5, 6, 7, 8.
So we're still
Okay,
counting.
1,
Starting.
2, 3, 4, 5, 6, 7, 8, 9, 13, 14, 15. So I, no, this one. Okay, so let's count now. Do I count this?
No.
Not yet. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So it is 8. It is the same. Okay, so this one we don't really count it, but can we move? Yes, because this one should really start here, right? So it is 80. It's the same.
80 to 90.
Yeah, it's 80 to 90.
Okay,
You agree?
yes.
One more time. Okay.
What I mean one more time?
Where you get that one.
Okay, so I established my 3-second markers. 3-second marker, 3-second marker.
Okay.
I did not count this initially, okay, because it's incomplete heart rate. So I counted 1, 2, 3, 4, 5, 6, 7, 8. I should not really count this because it's incomplete, yeah? So the T wave stops here. However, can I move it? Yes, because technically my marker started here, but it didn't, this heartbeat started here. So if I move this, then this would have been within my 6 seconds. Okay, so that's 8. So it's the same, 80 to 90. Yeah. Okay, do it next week. Okay, I sent you email already, so who's going where?